Okay. So I'd like to welcome you all to another installment of Quantum Fluids and Isolation. I'm very happy to introduce today Professor Tarun Grover. So Professor Grover got his bachelor's degree from IIT Kanpur in 2005, and he did his PhD at MIT under Professor Senthil Todadri, which he got in 2010. He did a postdoc at the University of California, Berkeley from 2010 to 2012. And then he was a postdoc at KITP from 2012 to 2016. And currently he's an assistant professor at UC San Diego, where he began in April 2016. He was the recipient of the Whitehead Fellowship at MIT from 2007 to 2008. He also won the Moore Foundation postdoc under EPIQS from 2014 to 2016. He won a Sloan Research Fellowship in 2017, and he won the NSF Early Career Award in 2018. And today he'll be talking about simulatable models of nodal superconductivity and Kondo breakdown. So please help me in welcoming, either by unmuting yourselves or by clapping virtually, Professor Grover.
Great. Thank you so much for this very nice introduction and for the invitation. And yeah, it's great that we can still do this despite all the lockdown. And thank you for being here. So this work is with my amazing collaborator. Xiaoyan Xu is my postdoc. Fakir Assad has been my long-term collaborator from University of Würzburg, and Bimla, Johannes, and Toshihiro are part of, or at some point they have been part of Fakir's group. Johannes now is actually postdoc with Erisberg, and Matthias Voigt, I hope, I'm sure you all know already. He's famous. And so, all right. So let's start with, so the references are here. You can look at them later. It's really I mean, I just put them there because it's being recorded, so you can go back and look at the video if you need them, and they're all on archive also. So, all right. So let's get started. So this is the outline. So I will first try to describe this so-called fermion sign problem in very brief way, and then discuss problems which I've been thinking for a very long time, questions about superconductivity, especially in strongly interacting systems, for example, in high fermions, and I don't know, cuprates, and those are very hard questions, and I don't see obvious way to solve them directly, but the idea here would be to perhaps just find some designer Hamiltonians which share some features with those phase diagrams. So I'll focus on two kind of problems. One is heavy fermion materials, perhaps which have Kondo screening or sometimes Kondo breakdown, and secondly on nodal superconductors in the presence of repulsive Hubbard U. So these will be the kind of problems I want to focus on, and they are paradigmatic. I mean, they are kind of well-known problems in condensed matter for a very long time. So since we have this somewhat new understanding of how to think about sign problem, it's or at least design new models, even if it's not maybe a very deep understanding, I would say. So it's good to go back to these old problems and see what we can do. That's the kind of motivation. So the first part of my talk will focus on nodal superconductors without getting them without sign problem and studying their competition with antiferromagnetism. Perhaps you all are familiar with this kind of materials, for example, cuprates, pnictides, and these are these organic materials. All of them have the feature that they are there's perhaps always some Mott-like phase, and there is also some superconductivity. So both of these things happen close by. So can we find some models which have some such physics? That's the motivation, and the kind of models I will focus today will be at half filling. So I will think of, so they are more closer to these organic materials where there's a pressure-tuned transition from antiferromagnetism to superconductivity. So these are So this is not a doping tuned, but pressure tuned Mott transition. And there are many such materials. I'm just listing some of them here. And there are a lot of data that the superconductivity is in fact nodal. For example, in thermal conductivity is power laws. So is this NMR has T cubed, which is signature of a Dirac-like node in many of these materials. So these things exist, at least in materials. And so let's see what we can do. So if we want to study them faithfully, we write down some macroscopic Hamiltonian, which typically resembles something like a Hubbard model. And then you soon realize that if you try to simulate these models on a computer, even a quantum computer, you can't do that, because these problems are so hard that there is no from just some complexity point of view, there are obstructions. And one such obstruction is so-called fermion sign problem. And this is kind of the fundamental obstruction for these Hubbard-like models. And so generally, you might have heard of this kind of introduction to this fermion sign problem, that the partition function looks like some sum of some bosonic weights, this modulus of weight, times some fermionic exchange sign, sum over all configurations with some boundary. Like if you think of world lines, you have to come back to the same place. So if you think of identical particles, it's a periodic boundary condition, but there is a exchange which happens of the world lines, which is allowed because they're identical particles, and for each exchange you become a minus sign. And if you write this in a computer, you will see that it looks like sum of terms which are oscillating very widely, and most of them are equally. It's likely to be almost equally positive and almost with equal and equally negative, with leaving out some exponentially small term which you're interested in. So this is one way to think about sign problem, and that's correct. But we already know there are models where there's no sign problem in the presence of fermions. So maybe this is kind of too fast, and so let me present just a statement without maybe a lot of proof. Is more like a conjecture. Let me put it this way, and I can make it more precise later if you are interested. But let me at least give a flavor of that statement. At least to me, the fermion sign problem is fundamentally about competition between what I will call Mottness and generic filling. That's the tension. And what do you mean by Mottness? Fermi surface we all know. So Mottness, I really mean that, consider, for example, a Hubbard model, and first let's turn off the hopping and consider some generic filling. When U is positive, system likes to have some local spin, non-zero spin on each side. And that's what I call Mottness. You have some well-defined local spin. On the other hand, when U is negative, on each side you prefer just zero spin, like just a singlet pair, and that leaves at any filling at zero chemical at zero hopping. And the kind of claim I want to make is when you're in this Mott regime at any generic filling, and it's important, it should be the filling to be, I don't know, e to the power pi or whatever, something which is some irrational filling, not some half filling or something, then you have sign problem. And that's the kind of tension. So, and it's sort of like anomaly, almost like that you have some local spin half is like anomalous in some sense, like in Lieb-Schultz-Matisse sense, and these Barry faces associated with this anomaly kind of make the sign problem basically hard to solve or impossible, I would say. So that's the problem. So also please feel free to stop me at any point, otherwise, I don't know, you may as well listen later, recorded video. There's no point of being here if you don't have the chance to interrupt and ask. So feel free to just do that. And Yeah,
Sorry,
please.
Tarun, can I ask a question? So
Sure.
the
Yeah.
the sign problem on the left, the non-mod picture, is it simply because that the two spins go together, and that
So saying why there's no sign problem in this phase?
right?
Yeah, because it's locally there's no spin 1/2, so it's like a bosonic system with zero spin. It has no Barry phase per site.
I see. But is it true that we always have pairs of spins like this when you use negative?
No. I think that's the key point was that I'm doing some adiabatic kind of argument. I'm saying first set t to 0. Then and then it's a classical problem. You can find a solution. Then
Right.
you find this is one of the ground state. There are many such ground state, but all of them will have zero spin. But I'm saying the kind of claim I want to make is that if you're in a phase where you can now if you turn on t, what I want to say is that the fundamental sign structure has not changed. That's the kind of argument I want to make. It's almost like kind of argument you make in anomaly flow, that you have some, if you have some anomaly, it remains invariant under some deformation, and that's the kind of thing I want to make. But I obviously didn't make it precise, but at least that's at least a broad flavor that in this regime Barry phases are not important.
I see. Thanks.
But all this heuristic, I've been thinking about it. I just wanted to still say it because I feel it is kind of important for thinking about these models, which we always kind of see which don't have sign problems. So so in the past there has been a lot of now work starting from bosonic system, for example, spin system. This term actually came from designer Hamiltonians, where you're designing Hamiltonians to get rid of sign, design them from I don't know, stochastic series expansion. People wrote down all kind of interesting models. I know Sandvik, Ribu, Melko, Adrian. I mean, all these people who have been developing all kind of new models, interesting models, and more recently, last 5-6 years, these things have kind of slowly entered fermionic realm, and so and this talk will be along those lines. So let's say the kind of so I will divide all models in two classes. One is, in one case you want mod physics, other case you don't. You want Fermi surfaces. As I said, there is a tension between them, so you have to pick your poison. You can't have both at the same time. So when you want mod physics, then the main problem will be that you can't have, as I said, generic filling. You'll be restricted to some specific filling. And for example, at half filling on bipartite lattices, so you need some symmetries. So if you do that, for example, so you might think, okay, I can still get Fermi surface, for example, on a square lattice, but you will find as soon as you turn on any repulsive Hubbard U, which is the mod physics, you will gap out the Fermi surface immediately. So it's not a stable phase. The Fermi surface cannot exist. So it's consistent with this tension. Or you can have like Dirac medal. Again, it's fine. There's no Fermi surface. On the other hand, if you want Fermi surfaces, then you will find that at almost always at ultra low energy, as far as I know, you don't find anything like mod physics. You can get perhaps S-phase superconductor, for example, or you can get some kind of fluctuations in which locally there is no spin. Perhaps there is some other object which doesn't carry spin. So that's the issue. It's, for example, so one very specific problem where you see this tension is if you want to obtain nodal superconductors. So nodal superconductors really require on-site repulsion. So they really require having repulsive Hubbard U. And you will find that these kind of models where chemical potential is arbitrarily tunable, as far as I can tell, you cannot get that physics. You can try it. I'm at least that's my conjecture. You will fail. So And people have tried, and they always find things which are not nodal. And they still may be confusing because we will still talk about in these kind of models unconventional superconductors, but they have sometimes two bands. One of the band has one kind of S-wave pairing, other band has other kind of S-wave pairing. Locally, they are on site, and there is some sign structure change when you go from one band to another. So it's trying to mimic something like D-wave, but it's really S-wave because it's locally you have no spin on a given site, and you don't get nodes correspondingly. So we are interested in nodal superconductors and its competition with antiferromagnetism, partly motivated from these experiments I mentioned. And the key point is if you're coming from thinking about cuprate experiment, you think of them being connected by some, I don't know, some kind of chemical potential. And as I said, that's hard, that we can't do because of this tension between Fermi surface and Mott. So instead, we will the main observation is neither of these phases require any chemical potential. You can have them at half filling. So why not just do that? So long ago there was a proposal for such a model. This is work by Facher and Imada and Doug Scalapino, where they write down Hubbard model and added this term, which is square of a kinetic energy on each bond, and they found some signature of a D-wave nodal superconductor, but I would say the signal is very small. So you can see the order parameter, it's about 0.01, and you have to still argue that it remains non-zero as in the thermodynamic limit and 1 over L going to 0. So somewhere you have to argue that this line is hitting a non-zero value. So it's not, I would say, I mean, unless you do very large sizes, it will be hard to be fully conclusive on this. So we were thinking of models which are somehow more kind of more robust to finite size scaling, or robust is the wrong word, but anyway, more, let's say, you can argue analytically basically that it will support a D wave. Let me put it this way, and then you can look at numerics after that. So so this is a model. So it has Hubbard model. So what's a Hilbert space? Hilbert space is electrons on sites and rotors on lengths. And so electrons which live on the sides of a square lattice, they have the regular Hubbard model, spinful electrons. It's a standard Hubbard model on a square lattice. Then you perturb that with two. So one term for these rotors, you write down just the X5 model for these rotors. So this is n and theta are canonically conjugate. And so nearest neighbor rotor bond is denoted like this. So you have all such nearest neighbor bonds. On that, you write down the cosine term and on-site charging term. So that's just the rotor model, X5 rotor model. And then you have coupling between the electrons and these rotors is done in a way so that e to the power I theta transforms as a Cooper pair. So that this is and tau ij's are just fixed numbers. They are on X bond, it's +1, Y bond, it's -1. So they are not fluctuating, they are not quantum. And so that's the model, and it has all the same symmetry as Hubbard model. We are not breaking any symmetry explicitly because theta carries the charge too. And of course there is spin rotation symmetry also. So it's just the same model as, I mean, in terms of symmetry, is the same model as Hubbard model, but it's just more complicated looking. If you like, this is like a Cooper pair. Basically, we are building in Cooper pairs directly, if you like. Think of theta being e to the power theta just being like CC. So you can think of everything being electronic, if you like, in some sense. And you can make that more precise at large scale limit. You can integrate out theta in that limit and obtain some other model which is purely electronic. So that's a model. So here you can understand this model analytically pretty much, because in various limits, for example, when J is large, you condense theta and you get there's a BCS mean field theory for a D-wave superconductor, nodal D-wave superconductor. So in that limit you have that phase. And in other limits, like in the usual, when J and K are, for example, small compared to U and T, you get antiferromagnetic insulator. So you have both the phases you wanted in some regimes. So the question is, what is a global phase diagram? So another thing, so the one thing you will notice just very quickly once you do mean field theory is that separating this nodal, this is just a mean field phase diagram. I will show Monte Carlo results soon. So we'll find always an intermediate phase, which has both antiferromagnetism and a gapped superconductor, which we call DSCG. So what is the physics of that?
This is all some fixed filling here. Did I miss that?
No, everything is at half fillings. That was the whole kind of main point, that we will stay at half filling, so that because if you had any non-half filling, is immediately a sign problem because of Hubbard.
Right. Okay, I just missed you restating that when you got to the
sorry. Yeah. Sorry, I should have said it. Yeah. I didn't write down this part clearly. Sorry. So this is all at half filling. So you have so this intermediate phase physics is very easy to understand. So first, suppose you go to the nodal D-wave phase and try to build in superconductivity. Because of the symmetries of this model, the nodes are separated by pi. That wave vector is pinned actually because of the bipartite lattice and this particle hole. You can't change this. So as soon as nail vector tries to condense, it gaps out these nodes. It does not destroy superconductivity. It leads to antiferromagnetic order, but also leaves some gapped superconductor. And this notation is from some old work, which I will mention soon. So there's always this intermediate phase. There is no second order transition between these two. And
Tarun, quick question.
Yes,
you have
please.
nodeless fermions here, massless fermions at the nodes?
In this nodal phase, yes, they are gapless fermions.
Right, so you will basically look at antiferromagnetic and phase fluctuations in the presence of massless
Exactly.
D-wave fermions, yes.
Exactly. And I will discuss the field theory soon about that.
Yeah, I'm curious.
Yeah. So now you can look at the finite size scaling. Now you see, without even shadow of doubt, you see D-wave superconductor, as you should, because we constructed a model that way. So you see, this is 1 over L scaling. This is a D-wave order parameter, clearly going to a non-zero number. You can do up till 20 by 20 sites. And antiferromagnetic order parameter also in some other regime. Don't focus so much on the precise what regime. You'll see the phase diagram soon. But the main point is, very conclusively, you can see both of these order parameters being non-zero. So then you can start looking at even spectral functions. For example, when in the nodal D-wave phase, you clearly see that they are nodes. This is AK omega plotted in some regime where they are nodal superconductor, like, for example, at small at small values of K over J here. And so this is the nodal phase. You see they are nodes in the fermionic spectral. So the top one is a fermionic spectral function. The bottom one is the spin correlation function. So you see that fermions are gapped at the K points. This is a nodes. This is same as these. There are these K points, and then they at some point become gapped, as I just advertised earlier, because of antiferromagnetic fluctuation. And eventually you get, once they are gapped, they remain gapped, and everything is consistent with what I showed in the mean field, and it has to be. Basically, there's no kind of ambiguity there. So this is the phase diagram you get from Monte Carlo. So you get a nodal D-wave phase, coexistence phase, and coexistence is not phase separated in any way. Just both things exist in order parameter at the same time. So, and then there's a regular antiferromagnet, and this is just the order parameter you see. The D-wave order parameter, the superconducting order parameter remains non-zero up till this point, and the antiferromagnet remains non-zero up till this point. So there are two quantum phase transitions. So sort of one of them is very easy. This is just because here the nodes are gapped and antiferromagnetism. So this is just across this transition is just XY, 3D XY, as you can guess. This one is more interesting because this is nodal superconductors. The nodal fermions and coexisting anti-fermion fluctuations. So this is more interesting. So let's look at that one. And then you find it second order, and you find some critical exponent by some scaling collapse for the order parameter as well as correlation length. And these are numbers which you should not take so seriously, because maybe 1 can become 1.1, 0.9, but it won't become 1.5. So errors are not that large, but it's like plus minus, say, 0.1 because of system size is 20. So you're not doing thousands of sites. But at least it tells you that it's some strongly correlated fixed point, because eta is large. So it looks like one of those Gros-Nebo kind of fixed points. And we'll see that it is very much like that. So this kind of transition actually was long ago studied in this paper. Basically, this is old work by Leon, Matthew, and Chetan. They were interested in, they didn't write on this kind of model, but they were writing some effective field theory which has similar content in terms of phase diagram and so on. So, and I can, if you're interested later, I can mention what the relation to zero gap is, and I don't want to kind of get distracted right now, but they have a fourth phase, which is basically a Z2 gauge theory coupled to nodal fermions, which they were advertising at zero gap. And we can also get that, but I don't want to get into that right now. So, and if you now write down the field theory, you will, just based on symmetries, you can write down. So these are the nodal fermions, which are Dirac fermions, and there are fluctuations of net order parameter. And based on the symmetry, you write down this term. And this, as you can see, this breaks global UN symmetry, this term, because both sides of the transition break this global UN symmetry. Both sides are superconductors. One is a nodal superconductor, it is a gap superconductor. So this term, so it doesn't look like maybe a stat. It looks more like one of the supersymmetric critical point, although this one is not supersymmetric because the content doesn't match up. The number of fermions is not same number of bosons, but it has similar kind of broadly side-dagger boson kind of coupling. So okay, so what we noticed that actually an interesting transformation one can do, some funny kind of unity transformation, which is easy to write down in the Majorana basis. It's actually some SO8 transformation of your, so the free Dirac fermion, as you know, doesn't have just SU. If they have 4 complex fermions, it's free. It's not SU4, but it's O8 symmetry, and you can use that generator of those, one of those O8 for this free to rotate it into actually standard Gros-Nebo Heisenberg class. So this is, so it actually, you can map this transition to something which you are more familiar with, and then you can compare exponents, and things then make much more sense, and exponents are consistent with what we know about this transition from various previous work, because this is a much more well-studied model. There's so much work on this. So sorry, I'm not citing the papers. Maybe I did earlier, and I don't know where it went, but this is a very well-studied model. There's a lot of work one of the well-known work is by Facher and Igor Herbert, and also much later works actually by bigger sizes. So our numerics results are consistent with those, but you have to realize this interesting transformation to conclude that. So there's a recent work which is it has some relation to our work, which is, I should mention that, which is this work by Otsuka and collaborators, where they directly looked at a BCS mean field Hamiltonian, which is this, which breaks global U1 explicitly and at a Hubbard U. So this is not a model for nodal superconductor, because you don't have the U1 symmetry to begin with, so you broke it explicitly. But the low energy theory of this transition, this specific transition, will be same as what you will get here, because both sides of the transition break the U1 symmetry, so it doesn't matter even if you break it explicitly. So that's why I would say this may be a more efficient way to simulate these kind of phase transitions, because you don't have to worry about this fluctuating field which we kept because we were interested in a real superconductor which has this actual phase fluctuations and so on. But if you're only interested in low energy theory at this transition, then this is all right. So any questions for the first part? So I'm done with the first part. So I'm seemed like right on time, half an hour.
But 20 by 20 is still pretty big here. Are there any, what are the tricks to get 400 sites?
I think it seems like just a luck. I think we have looked at other models which are very similar. We had a proposal for a deconfined critical point between a F-wave superconductor and it's not published, but and a nail phase where there's a direct transition because of Berry phase terms, and they really struggled to do very similar model, just slightly different lattice, honeycomb lattice, but we couldn't go beyond like 14 by 14. Even there, I don't have a good answer. I think that's the short of it. Sometimes you get lucky and error bars are small, and sometimes you don't. I don't have any deep understanding really. But I think this is the biggest you could do as far as I can. I mean, I think we had to push. I mean, a lot of earlier data was on just 14 by 14, and then we became more sure which part of space drive to look at, so we ran larger runs on those. So that's the first part, and second part will be about.
Tarun,
yes, please.
Just a question. I'm a bit hesitant.
Mm-hmm.
Well, I'm not sure whether an answer is possible. I presume this is determinant Monte Carlo, right? Final
Yes.
Yeah. Do you have any knowledge about the density of states at zero energy, say either thermodynamic or?
I think we added like from AK omega you have density of states. This is AK omega.
Now the trouble is, I guess,
spectral function.
because of the big rotation, right? You're not very accurate at low frequencies and final
right. It's a good question. How to look at
the usual trouble, right? That you have the big rotation on top of all the other trouble. When you have dynamic information, then it's tricky.
I think you have equal time correlation functions without any problem.
Yeah, but it's not so useful, I guess.
But for
especially like to know the quasi-particle density.
No, but we did do. I think
Fermi energy.
So we did. No, we do have that maybe in the appendix. So that requires, it's a bit tricky because we have to do some kind of analytical continuation. Yeah. So we did that. So we looked at first unequal time, imaginary time correlation function, and then did analytical continuation using this
unequal time, right?
Unequal time using this maximum entropy methods, and you get consistent. I mean, you see similar physics as we expected. For example, when you're close to the transition, you see that the spin spectral factor is much more broad, so there are no quasi-particles. And then you go away from it.
But they leak out to zero frequency. Right? Basically, it's a question whether the zero temperature fluctuations may actually decohere the nodal fermions. That's a question.
But they did, right? That's why
final temperature is obvious, but
no. This I mean, at zero temperature, this exponent eta is at zero temperature, and this, as long as eta is non-zero, you will find that fermions there are no quasi-particles because there's a branch cut rather than a pole. So that we know. Yeah. And that is conclusive because that requires only equal time correlation functions. If there's even that's enough because it's a relativistic theory to begin with, so you already know what happens.
I hear what you're saying. Yeah, thanks.
Yeah. But let me say one broad point about this thing. The surprise here is not that we have a nodal devious superconductor in this specific model. I would like to emphasize that. The surprise is it doesn't have a sign problem. I think that's the message, because you can try all kinds of things. It's very hard to find a model which has a nodal superconductor. People have tried and it's hard, and it just somehow this one works, and I think that's the kind of new thing here. I mean, because once you stare at this model, it's not maybe obviously clear that it doesn't have a sign problem, but it's just the way anti-unitary transformation works and so on. You get lucky. If you try some other one, for example, if you try a triplet or something, you'll find it's a sign problem. It's just I have some intuition why this one doesn't. We can discuss at the end, but that's the new thing. So the second part of, as I earlier hinted, second part of my talk will be mostly about Kondo physics, Kondo breakdown, and this is the famous Donny and phase diagram. antiferromagnet to some heavy Fermi liquid. This is like a, I don't, this one phase is like a, if you like, spin density wave. Other is like a Kondo phase where you form local singlets and leftover fermions from their small, from their large Fermi surface. I mean, overall it's a large Fermi surface if you do the Röttinger counting mod 2. So this is, yeah, that's the physics. And then there's been a lot of recent work on experimentally trying to find models, materials where this paradigm sort of fails. There are new phases people find, which are neither this or this, at least. And that's not surprising. Real world is obviously much more interesting and much more, I don't know, rich. And so some of the kind of things people have found is what seem like partially Kondo screen phases, where they found on a Kagome lattice, for example, some spins order, but some seems to be completely, I don't know, paramagnetic, if you like. They don't have any, I mean, they kind of don't have any local spin left. So either they are Kondo screen and perhaps maybe they form a spin liquid. No one knows really, and it's not conclusive. But recently there have been claims it may be like a spin liquid in some regime after you apply some magnetic field, this material, this cerium, palladium, aluminium. And then there's this old work, as you might have recalled from, I don't know, 10, 15 years ago, this germanium to ytterbium rhodium silicide, where there was a claim of intermediate small Fermi surface phase, similarly with irium dope. So there's a lot of, at least phenomenologically, there are systems where they seemingly either a small Fermi surface without any, I mean, by which I really mean there's no magnetic ordering, and then there's this partially Kondo screen phases, and at least in this case, it's clear that geometric frustration is playing some role, because these are Kondo. This is like a Kagome lattice, and we can write down models based on what we know microscopically, and they are frustrated. So based on that, so the two kind of axes I would like to explore. One is if you have a Kondo coupling in the presence of geometric frustration, things like this, or Kondo coupling when you reduce dimensionality, perhaps. And this is another way to get some new physics, which goes beyond this Donier phase diagram. For example, you can take a two-dimensional electron gas, for example, some copper, and then like you can put atoms on it, on top of it, add atoms, which carry spin. So it's like designing Kondo lattice models where there's a dimension mismatch between the local moments and the conduction electrons. And you will find again some new physics here. I will discuss. This is again you will find some analog of fractionalized Fermi liquid here. So let's first go to the first one. And I think I am somewhat running behind time, but let me try to focus on the results. So first I explore geometric frustration. So when you have geometric frustration, there are two sources behind problem: Fermi surface and geometric frustration. Focus on just this, I don't know, these main words. Don't worry about this Hamiltonian, but as you know, geometric frustration also causes sign problem, but we know sometimes it doesn't in some spin models. For example, Kitaev toric core doesn't have sign problem. So we know there are ways to get around sign problem and the geometric frustration. And let me skip this. You know how bosonic sign problem occurs. So when the off-diagonal elements are not negative, you get sign problem. So the sort of main idea which we found is that you can understand bosonic sign problem from a completely fermionic perspective if you employ spin-ons. So you can map this kind of criteria, which is about off-diagonal elements being negative or positive, in terms of some determinant sometimes. And so the advantage of this is then you can, if you write this representation, then you can study Kondo lattice models and add frustration of the kind which does not cause sign problem in SSC. If you don't do that, then there's no way to simulate these kind of models. You can't directly combine SSC with determinantal Monte Carlo because they're operators. It's not some diagonal coupling. It's not like the kind of coupling recently people have explored where you couple, let's say, just the Ising component of some object to some C dagger C. Then you can work in a basis where, for example, the Ising, because of Ising coupling, you can combine SSC and determinant Monte Carlo. And this is the kind of stuff, in fact, we did in the D-wave problem, for example. You don't have to, there's a rotor in the earlier model I just showed, and then there is a fermion. And you don't have to do any of this. You don't have to write a rotor in terms of some fermions or spin-ons. because there's a coupling is almost like it's diagonal. It's just c dagger times e to the power I theta. So if you work in the theta basis, it just looks like a number. But in Kondo lattice models, if you really want to explore Kondo physics, you require at least some global continuous symmetry like SU2 or U1 at the very least, and then you can't do any of that. So that's why you have to employ this slave particle technique, and you impose f dagger f equal to 1 exactly. So it's not approximation. We are not doing some slave particle mean field. It's the exact rewriting. You have the correct physical Hilbert space and so on. So let me just show one model. I will just focus on the results. So we wrote on a model which has geometric frustration of local movements. So the electrons, just you can listen to my words if you don't, it's a bit hard to maybe follow this figure, but it's electrons live on the honeycomb lattice because we don't want Fermi surface with repulsive Hubbard U. And the local movements also live on the honeycomb lattice. So, but they have geometric frustration because honeycomb lattice is like two triangular lattices. You add those SZ coupling on those triangular lattices. And then there's a Kondo coupling, which is C dagger sigma C dot S between these two. So each site has a fermion at half filling and a local movement, and local movements are frustrated. And without frustration, this model has been well studied. You just get a Kondo insulator in one side, and you get antiferromagnetic insulator on the other side with O3 critical point in between. And the main point is that when you add this frustration, this y-axis is the frustration, you get a completely different phase diagram. Like whole part of the phase diagram, I mean, large part of the phase diagram has nothing to do with this Doniec-like physics. You find a partially Kondo screen phase where some sites have large spin, some have small spin. If you like, it's like a ferry or antiferromagnet. I don't know if that's the right word, or it's like an antiferromagnetic ordering of some kind. But with different moments on different sites. And there's some slight different analog of this partially Kondo screen phase, which we call ZPKS. PKS is partially Kondo screened, which we call XYZ PKS, but I won't get into that technical detail. But let's just focus on this ZPKS phase. The main point is, please, yes.
Just pure clarification. These are Ising spins, right?
These are not Ising spins. These are SU2 spins, but the coupling between spins is Ising. So the global symmetry is
oh yeah,
global.
that's what I mean. Yeah.
Global symmetry is not Ising.
Interaction is Ising.
Interaction is Ising, but the global symmetry is U1.
I guess that's an issue, right? Because you may expect very different physics when it's Heisenberg.
Of course, you will expect very different physics if you're Heisenberg, but coincidentally, in this specific material, the cerium, palladium, aluminium, sorry, I don't want to go this. In this material, people have, microscopically, it's actually because of some easy axis anisotropy, because of some microscopic, it's actually Ising.
Yeah, so, I know. Yeah, so it's really nothing to do. The other technical thing, I would think it's extremely hard to accurately compute the frustrated Ising spin system with Monte Carlo.
Sorry?
I would think it's very hard work to compute the frustrated Ising spin system by itself.
Yeah,
with Minneapolis.
It's not easy, and that's why it took. I mean, it just takes. You have to. The thermalization times become very long, but there's no sign problem. So at least you can. If you wait long enough, put enough CPU hours into it, you get accurate results. So the error bars are smaller than these. So it's not easy. It's not like you can do it, I don't know, in one night. It may take a month or two, but it's doable.
Goody, I got scared that you guys had invented a trick to solve the spin class problem, right? That would be horrible.
You can, I mean, we did that, and it's.
Yeah,
I mean, there are parts of the phase diagram which are inaccessible because of such issues, but most of the phase diagram you can figure out.
Frustration, I guess.
Yeah. So because of this frustration, you get this partially Kondo screen phase. Rough physics is that if you add on a given triangle, for example, look at this A sublattice, the sum of spins is 0, which is the effect of this frustration, and the B also is 0. And the main point is, which I want to emphasize, is that this specific, you might think spins are ordered, so it will just gap out fermions because of some fermion mass. But if you look at the effective in field theory, what is this term corresponds to? It's actually not a fermion mass. It only drifts the fermions around. It just drifts the nodes around. So the mass that is generated is because of Kondo physics. It's a non-perturbative mass. So that's an interesting physics, and you can see that in numerics. So this is an interesting phase. It's not like a regular Hertz-Mills kind of phase. Kondo physics plays much more important role. So, and then you can also study this partial Kondo screening using entanglement. And this is interesting because, I mean, we have been developing techniques for calculating entanglement for the last 10, 15 years. Now it's coming to kind of stage where you can really try to understand such complicated physics using entanglement. So that this is later work by Facher and collaborators, where they look at mutual information between the local moments and the conduction electrons, because that's the physics of sort of Kondo physics. It's about entanglement between these two, or breakdown sometime. And they clearly see that in the if they go along along this axis 1, where there is no geometric frustration, entanglement is log 2, and then it's almost 0 in this phase. But if you go in the ZPKS phase, this partially Kondo screen phase, entanglement is not log 2. It's actually smaller because of this partial Kondo screening. So this may be too much detail, but let me come to the next point. So how am I doing on the time? I guess I'm running behind by a lot.
I think you have about maybe a good 10 minutes.
Okay, yeah, 10 is good enough. So the another thing I want to another topic along the same direction is fractionalized Fermi liquid, which also, I mean, this is a different kind of phase which is motivated by this. I mentioned this experiment on iridium or germanium doped ytterbium rhodium silicide, where you find this intermediate small Fermi surface phase, seemingly. I mean, at least that's the claim. And we want to understand, can we simulate some of such physics in numerics without sign problem? So this was long ago. This Saintel Voita such they proposed this fractionalized Fermi liquid scenario where the local moments form some spin liquid. So they are doing some RBB motion, and conduction electrons basically decouple from it, and they form a small Fermi surface. And the question is, can we realize such model, a model which has such physics without sign problem? And you can. So you have to work with this fairly complex model called Jervin Balance-Fisher model, which has frustration, Ising-like frustration with nearest neighbor ferromagnetic coupling on a Kagome lattice. So spins liquid on a Kagome lattice have some geometric frustration. Don't worry so much about details, but it has enough frustration to give you a Z2 spin liquid. And then because of our tricks we developed for Kondo physics, we can add fermions in and do some kind of Kondo coupling. It's somewhat unconventional Kondo coupling. Some sites is ferromagnetic, some it's antiferromagnetic. We needed that to get rid of sign problem. So that's somewhat kind of technical issue here, but at least you can realize the small Fermi surface phase, which is non-Fermi liquid. So, the main upshot of this is we can get a phase which violates Luttinger theorem. It has small Fermi surface. In fact, size of Fermi surface is 0 in this case. When it is small, it's actually Dirac fermions. If it's a large Fermi surface, it will be not a Dirac fermion based on this. If you do mean field theory or just Luttinger counting, you can look at the and that's basically the physics. Phase diagram is so if there is no Kondo coupling, that's just decoupled system, which we know everything about. It has a Z2 spin liquid phase at large frustration, and the idea is now to couple it to fermions, and we can get this fractionalized Fermi liquid phase, which violates Luttinger theorem. And you can study again mutual information between electrons and local movements, and confirm that in this Luttinger liquid violating Luttinger theorem violating phase, you don't have the entanglement is basically 0 between electrons and local moments, and that's fun to diagnose. For example, this is the entanglement going along. For example, if you go like this, up to some point, entanglement looks basically 0, and then it becomes non-zero. You can do it this way also. So it's pretty robust diagnostic of this small Fermi surface. And you can also study critical point. I don't want to maybe spend too much time, but at a critical point, based on field theory, you can argue Kondo coupling is not relevant. This was actually done long ago in this work. And it's hard to see this numerically because system size are fairly small, and it's related to the comments by Jan about these systems are not easy to study. We can't do like 100 sites. So studying critical scaling is not going to be easy because of this geometric frustration. But at least the phase diagram, phase boundaries you can find. Critical properties we don't know so far, how much, which require much bigger size. So I think we don't have much progress on that so far. So the last part, in last 5 minutes, I will discuss briefly this this other axis to get unconventional physics, which is beyond this Donier-Case diagram, to consider mixed dimensional systems. And it's motivated by this actual experiment, and that's how we got started. And then we realized it has some interesting physics of fractionalization. And the experiment is basically you put some add atoms on, like magnetic add atoms on some two-dimensional gas. You can arrange them. There's two different groups have done this. And then there's also another, before I get into numerics, there's another experiment which is three-dimensional metal, which seems to have one-dimensional spin-ons. And it's a good metal. And it's somewhat surprising that it doesn't have Kondo screening of these spin-ons. So there's some material, it's a ytterbium, platinum tin, and then it has this, a lead, and that it has this this 1D chains which sort of decouple from the whole electronic bath around it, and you find very much like physics of spin-ons. And same thing happened in this experiment. They found evidence of spin-on-like features. So the model we write down is based on this. So Farker and collaborators, they looked at this experiment and tried to obtain all the microscopic parameters and match at least the local physics correctly, and wrote down this simple model where conduction electrons live in 2 dimensions and spins live in 1 dimension, the local moments. And then there's a coupling, Kondo coupling locally between the conduction electrons, and that's the standard lattice you will construct. But they obtained these parameters and confirmed that this is the right model based on all the data experimentalists had. And so we thought, okay, let's just study the physics of this model in one case where we could make a lot of progress, where we assume that the conduction electrons are actually Dirac fermions. You might not like it because actual Hamiltonian in the experiment doesn't have Dirac fermion that has full Fermi surface, and we are also studying that. We already have a lot of results, but I don't have time to discuss that. This one was more like a warm-up exercise, if you like, but it already was very interesting. So here we have to get Dirac fermions, we considered pi flux square lattice and add this Heisenberg chain on top. And the low energy theory will be interesting. It's some 2D system coupled to a 1D spin chain. And it's somewhat non-trivial to study it because if you want to do RG, both systems, that is a spin chain is strongly interacting. It's a Heisenberg spin chain, but we know everything about it, so we can do conformal perturbation theory to understand this RG flow. And then you find that Kondo coupling is actually irrelevant at the decoupled fixed point. That leads to a stable fractionalized Fermi liquid, which is, maybe that's a word not used often for this kind of system, but it is fractionalized in the sense that it has local moments which have spin-ons decoupled from conduction electrons. So this is the stable phase. And then there's a Kondo breakdown critical point separating it from a Kondo screen phase. The novelty here, which I want to emphasize, is that it's very hard to get physics of heavy Fermi liquid typically because of sign problem. Like this, even this Kondo screen phase is actually very non-trivial if you think about it, because of sign problem. Often you don't have such phases. The point here is that because of the dimensional mismatch, you can get that, and it's somewhat non-trivial. And there are extensions of this which we are studying, which actually confirm this intuition that there is a lot to explore with these kind of models. And you can do RG and you confirm all this. So I don't want to belabor that. And you have to perturb around some D. So epsilon is D minus 3/2 epsilon expansion, and physical case is epsilon equal to 1/2, which is very nice because typically you have epsilon is set to 1, you set to 1/2, which I like. So, and then you can confirm this phase diagram basically that at small Kondo coupling, you get decoupled spin chain, basically it dynamically decouples, you get spin-ons, and you can see even spectral form factor. This is all obtained using imaginary time and then analytical continuation. At small Kondo coupling, you have spin-ons. At large Kondo coupling, spin-ons are lost. So, so that's basically I wanted to say about this. The broad message is that there is this unconventional phase which has well-defined spin-ons and conduction electrons coexisting, and at some point you lose that physics and go to heavy Fermi liquid phase. separated by some interesting critical point, which has some non-trivial critical exponents and so on. So, so the very last part I want to kind of point out a kind of a new direction, thinking about such phases where maybe there's a coexistent spin liquid with a Fermi surface, like this small Fermi surface fractionalized Fermi liquids from an entanglement perspective. Is there something more universal you can say beyond some mutual information kind of thing, which has mutual information is not the best diagnostic for universal physics because it gets polluted by classical correlations and so on, and it has a lot of things which are not nice about it. So we want something else. So the idea is basically this: suppose you have a fractionalized Fermi liquid, which has small Fermi surface coexisting with zero spin liquid. Its entanglement will look like leading term will be L log L because of Fermi surface, and then there'll be subleading term which perhaps hide the topological order. And no one knows how to extract that, as far as I can tell, because this term cannot be cancelled out by any subtraction scheme, because it's a term from the low energy physics, IR physics. Whatever you do, Kitaev-Preskel scheme, Levin-Mann, whatever you want to do, it will never it will remain there. So how to get rid of this term? So what we are exploring now is to do projective measurement of electrons, that you measure the electrons everywhere and get a new wave function, which is purely spin wave function. And the claim is when there's a dynamical decoupling of degrees of freedom, this projective measurement of electrons will completely get rid of L log L and leave only a purely topological entanglement entropy, the subleading term. And anyway, this is a conjecture, and there is some argument you can make from field theory this will happen. This is partly kind of, if you think about recently, there's been work on these hybrid circuits with projective and unitaries. It's along those lines, some of these things. But let me show one example where we use this, a toy example. Consider there's a model of bosons which carry spin 1. So it has both charge and spin. Bosons carry charge as well as spin 1. And it has two phases. One is a Luttinger liquid of charges, plus the spin degree of freedom are in some trivial SPT phase, and separated from a phase which has spin degrees of freedom are actually in a Haldane phase. So, and they decouple at low energy from the charge. So that's an interesting thing. It's almost like a, if you like, it's like a, I don't want to use SPT star. I don't know what's the right word. I mean, okay, it's not, I don't have a name for it, just gapless SPT. But it's a phase which has SPT order coexisting with Fermi, coexisting with 1D gapless fermions, 1D gapless Luttinger liquid. So, yeah. So how to see this physics of SPT hiding behind this Luttinger liquid? That's the question. So this is work with Daniel Benzine and John McGreevy. We did recently, and we are thinking more along this direction, and there's actually a lot to do. And but let me just show one thing. So if you don't do any projection of this gapless degree of freedom, so but without projection, I mean it's just the actual wave function. Look at the entanglement spectrum. It looks very much like a CFT spectrum. It's very hard to see anything about SPT or non-SPT. And then you do projection. You just measure all the charges, leave the spins quantum mechanical, do whatever they want to do based on bound probabilities, and you will start seeing these are three different couplings. All of them are in the gapless SPT phase. I should also show this. I don't have the data right now, but it's in the paper. You can look it up. You don't find any. So you clearly expose the edge states with this projection, and you start seeing physics of a gapped Haldane spin 1 chain. So this idea works, and I think it's interesting direction to more generally. It's very interesting to think about characterizing phases of matter, ground states, by doing partial projections or of these kinds. And if you look at this paper, we derived some general results for those things for ground states using inequalities from strong relativity and so on. So but there's a lot to be done even now. I think it's a whole field, I think, but it's yeah. But I don't have more to say on this right now. But this is all. So that's my talk. And so the broad message is that it's possible to construct sign problem-free models, which sometimes allow some simulations of seemingly very hard problems about Kondo breakdown, non-Fermi liquids, nodal superconductors, and so on. You have to just kind of think about what is the main you have a problem, you kind of try to understand what you can give up without kind of spoiling the whole physics, and whether the giving up gets rid of sign problem. And so that's, and then we also have a model dimension or deconfined criticality, is still work in progress. We seem to find a first order transition that's not great, but it's but from field theory it's allowed deconfined critical point, and there's no sign problem. So we are still thinking about it. And then there's very interesting direction of 3D matter coupled to 2D local moments. It's already Farker has already started working on this, and we are exploring this. And then Kondo breakdown in the specific material, and more generally thinking more deeply about sign problem, the kind of stuff I earlier mentioned about is anomalies and so on. I think there's things to be understood there, but at least there's some concrete conjectures I can make when there is sign problem and there isn't, and so on. But so far it's consistent with everything we know, but I don't have any kind of derivation of those conjectures. Or anyway, yeah, so that's all. I think I will hope we should maybe take questions.
Okay, so if anybody has any questions, they can either just unmute or they could raise their hand.
Drew, thanks for a very nice talk. You fit a lot of different directions and different models in here, but it was really, really nice. For the first system, this deconfined criticality in this model, which, I mean, as you said, because of good luck, maybe one can study very large system sizes. What else do you think you can learn there? I mean, what's
right.
the
So
prospect for learning?
There's so much to do there. So the one thing we notice, I mean, okay, maybe everyone can know it once you know this model, it kind of obvious maybe after once you have seen it. You can add magnetic field without sign problem. Any orbital magnetic field, like you can do the pi substitution and there's no sign problem. So you can drive even a transition from a superconductor to some non-superconductor by adding magnetic field. And in principle, if you have some super powerful computer, maybe you can start studying physics of, for example, abricos of lattices and so on, right? That's very hard generally. No one has, to my knowledge, has studied those in interacting systems ever actually, because nodal superconductors have not been studied, to my knowledge, in numerics without sign problem. And this is one direction about magnetic field. Other direction is, as I mentioned, this paper by Balance-Fisher and Nayak, where the motivation was a pseudo gap phase, and you can study that also without sign problem. Basically, you have to add enough frustration for this bosonic fields so that you enter some, for example, a Z2 spin liquid, which has gapless spin-ons, and you can get that without sign problem. Based on, we can write down those terms. There is no sign problem, and we kind of know what to do. But it's just a lot of work, and we didn't do it. It's some whole other project. We haven't had time to get into it. But you have to add some ring exchange term for this theta, which doesn't have sign problem because that's a diagonal term, and you can get what they were thinking of a candidate for pseudo gap. It's it's broadly along same direction as people have been thinking for pseudo gap using fractionalization for last 20 years. I mean, there's a lot of work by Subir, as you know. It's along those broad directions. This kind of pseudo gap phase, it has similar, I mean, somewhat similar physics as in very broad terms. Broad motivation is similar, so you can get that kind of physics also. And what else you can do?
That's enough for now.
Okay, yeah, but
thanks.
Okay, any other questions?
I have a bit of an open-ended question. Maybe it's more, you can choose in what way you want to answer it.
Sure.
So it's about this. I mean, you've tried to construct a model which has some features that you want, right?
Right.
For example, so the whole idea is to have some kind of, I don't know, some superconductivity or some antiferromagnetism, and the only constraint being that you don't want to sign problems, right? So,
right.
And in order to do that, in some of the Hamiltonians, you had to do some things which wouldn't be obvious what it means microscopically. For example, you showed a model in which you added a term which is the square of the kinetic energy. So
right, this is this work by Scalapino for example.
Yes, yeah.
Right.
So is there a way to, so my question is as follows. Is there a way to make a connection to like some particular, you said like, you want to talk about some particular material like yttrium.
Sure. So yeah, here the motivation for them was actually strong coupling to phonons. It should couple to some like energy coupling. So this is symmetric under all symmetries, this hopping term. So if you integrate out phonons, you will start generating such terms. And that was their partly the motivation. There was some around that time, this 1996. I'm sure I think there were some experimental papers which are suggesting coupling to phonons, which keep happening on regular basis in cuprates, and they were partly motivated by that. And I think I wouldn't personally. My perspective is that try to focus on questions which are maybe universal, which do not depend on such microscopic arguments. Some question about either whether you have some phase of matter in mind and you want to study its universal properties, or you have some critical point in mind you want to study its universal properties. And that's the kind of perspective I want to take. Or more broadly, topology of the phase diagram. For example, these experiments have basically the same topology as our phase diagram. So for example, look at this one. This is antiferromagnet. There's a coexistence of antiferromagnet and superconductor, and then there's the unconventional superconductor, which is nodal D wave. This is basically the same phase diagram as I showed you in our model. So the point is, once you have built in some such physics which has, if you have a model which has same symmetries and same filling, then it's based on our experience from all kind of everything that we have done in last 100 years, things often look very similar. Things are sort of, in some sense, universal. Even the topology of phase diagrams tend to be universal if you have the right symmetries and, I don't know, if you like, in modern terms, right anomalies and so on. So then it's so that's the kind of perspective I want to take, that you try to match those things as much as you can without having sign problem.
I see.
Yeah, if you are interested in a specific material, typically every material will have some term which causes sign problem, and it's but question is whether it's important or not. Can you not have that term? And for example, nail antiferromagnet, right? Nearest neighbor nail antiferromagnet has no sign problem, but any real material probably has some diagonal term which causes sign problem while remaining in the same phase of matter. Does it mean that we don't understand those material at some level? I would say no, because I would say that we understand the universal physics. We understand that term doesn't do much up till some threshold, and we are happy with that typically, with understanding, for example, physics of Goldstone modes. Or if you want to understand much more, okay, you want to understand more detailed perspective, then okay, then maybe you have to do DMRG, or maybe you have to, and recently there has been more work along these directions. If you have some terms which cause sign problem, but it's not kind of fundamental in the sense that phase can exist without sign problem also. Perhaps some short depth unitary circuit which connects the ground state of your sign problem free model to a model which has a little bit of sign problem. So that's another direction which needs to be explored more. This is, as you know, there's work by, I don't know, Roger Melko and collaborators, and Jan Zeisert and collaborators. So I think there's a whole other direction of, starting from the designer systems, and then maybe do short depth unitary and maybe combine that with Monte Carlo, and that hasn't been explored much. So,
yeah. Thanks for your answer. Yeah.
Any other questions? So maybe let's thank Professor Grover again.
Thank you for being here, and